Okay students, so today we will study the concept of residual entropy. To study this, first look back at the third law of thermodynamics, which is represented by this equation that limit t approaches 0, S is equal to 0. That means entropy of the system is 0, or rather correctly approaches 0 as the temperature reaches 0 Kelvin, that is T is equal to minus 273 degree Celsius. So, in simple words, at T is equal to 0, then entropy should be 0 as in science, but this is not the case, as there is always some entropy left even at 0 Kelvin. This entropy is termed as residual entropy. That means the entropy which is left over. It can be noted that every element exists in crystal form at 0 Kelvin, because there is no gas or no liquid as temperature is very low. Now coming down to the mathematics, by definition entropy is given by S is equal to K log of W, that is S is our statistical entropy, K is Boltzmann constant, and W represents the number of ways by which molecules can align in a crystal lattice. Now crystalline carbon dioxide, carbon monoxide or water as well as hydrogen have shown to possess non-zero entropy at 0 Kelvin. That means they all have what we call residual entropy. Now, arrangement in crystal lattice causes residual entropy. To explain this, consider these two systems. In the first system, all carbon monoxide molecules are perfectly arranged with respect to each other. That means there is a perfect arrangement, whereas you can clearly see that in the second sample, green and blue colored molecules, they are in different arrangements. That means there is no actual proper order, or there is a small degree of disorder. So this small degree of disorder, this causes residual entropy, as we know that entropy is nothing but a measurement of the disorder in the system. Next, coming down to the calculation of residual entropy for numerical problems, we start with S is equal to K log of W, but for 1 mole of a gas, the Boltzmann constant is always equal to the universal gas constant. That means we can write S is equal to R log of W. This equation we will use for the calculations and in the numerical problems, where W is the number of ways in which molecules can arrange themselves in a crystal lattice. Now, for a sample problem, a molecule X can have 4 possible arrangements of similar energy. The problem is calculate the residual entropy. So, what we need to focus is molecule can have 4 possible arrangements. That means we are given W is equal to 4. So, what we will do is we will put this value S is equal to R log of W, that is 2.303 R log of W. We have converted natural log into log base 10, substituting the values 2.303, 8.314 into log of 4. So, what we get is 2.303 into 8.314 into 0.6021, which is the value for log 4. What we will get is 11.52 joule per Kelvin. This is the value of residual entropy.